this control panel goes out of my way. Okay, so thank you, Pallavi, and thank you, the organizers of iLEAPS, to give me this opportunity to talk about our understanding of the regional emissions and removals of greenhouse gases. As was introduced, I am Prabir Patra, working in Jamstech in Yokohama. So I'll straight go to some introduction. In this case, is that, so this is kind of a very popular diagram now. You must have seen this several times, which shows that on the right side we saw many different species and their contribution to the global surface air temperature change, or GSAT, in the period from 1850 to 1900 as a reference, until now in 2010 to 19, the most recent decade of IPCC AR6. So what we will see here, that we consider these three, carbon dioxide, methane, and nitrous oxide, as the major greenhouse gases. I will focus today mainly on carbon dioxide because that itself is complicated enough to be spoken in one webinar. So and then of course we should understand, or we should analyze them when we are talking an assessment of like IPCC. So we also study all the species. They're sometimes referred to as SLCF, short-lived climate forcers. That includes methane, and they are also like you might know that they are also like air pollutants. So when you talk about this climate mitigations, we also have a chance to reduce air pollutions, which means the co-benefit for us, and a different chapter handles of the air pollution aspect of it. So what happens in this case is that we run these simulations using Earth system models, and as you see from this diagram, some are positive and some are negative. The negative is kind of the sulfur dioxide. When you are there under the flying in the atmosphere, they kind of blanket the incoming solar radiation and then have a negative, and then as a whole. So when you add all of them together, we can get the total simulated contribution to the global surface temperature change from the all human influences, and then we can compare that with the observed temperature change. So we come in the very, very close agreement in terms of the absolute value and also the uncertainties, which means that the level of understanding of the global climate system has improved significantly in the recent times, and CO2 is a center of the attention for us in this case, because it has a long lifetime. And to give you slightly more history, like how these calculations are done and how this greenhouse effect is calculated by the models, is that we define a term called effective radiative forcings. They are counted as watt per meter square unit, and with time we can simulate them, and these are the things we see, the balance of the sun incoming radiations and outgoing radiations from the earth as a balance of the net energy budget of Earth's atmosphere, which is a very, very fine balance. But these small numbers of perturbations which are of concern as a global warming are coming from the greenhouse gases mainly. So this figure is mainly from the working group, IPCC working group 1, figure TS9. But what I did in this case is that we removed the volcanic activities from the this plot so that it looks cleaner. And as you focus on the greenhouse gases, they are continuously increasing for CO2, and then you can see methane into halocarbons, and then this is the aerosol components. So what you will see here is that in the past, going up to 1970, let's say from 1850, that aerosols are actually helping us to cool that Earth's atmosphere, and it is actually it reduced a lot of effect of CO2 warming, which is blue line here, and into the total greenhouse gas warming. But since 1975 or so, the aerosol cooling has been flattened out, or even reducing. So then you can see that as a net effect, we see an amplification of the very fast rise in the global warming in the last 50 years or so. And so these are the thing, all things we have done in IPCC, and then the reports are out, you can read them. But what I will now go into is details of the what happens to the carbon cycle, and how we understand the carbon cycle in terms of the processing and exchange between the pools of carbon, and how that could feed back into the climate systems. So before I go into details, and I think I wanted to show you some of the terminologies we use. The units particularly, we use parts per million, so then can be also defined in percentage, but it is convenient to use ppm, and it is used here, and also parts per billion sometimes is used. And we also use kind of a petagram of carbon unit, because a lot of CO2 are going to be emitted to the atmosphere. So a petagram is 10 to the 15 grams. Sometimes we define in the carbon unit, or sometimes in the CO2 unit, but they are very much exchangeable. So it just depends on the use of the applications we are talking about. So and now one of the things we try to prove in the IPCC, or even our own thing, is that whether the recent increase in the CO2 concentrations are coming from the anthropogenic activity. Because if it is not coming from anthropogenic activity, we need to do different things. If it is coming from the anthropogenic activities, the process, the method to reduce these concentrations will be different. So that's a very fundamental to our understanding. And we saw that the reconstruction of the concentrations of CO2 and methane and N2O going back to zero AD, in the beginning of the AD, which means that and you can see that before, like industrial revolutions about 1750 or so, the concentrations are rather fixed and they're not changing so much. But in the recent times, since like 200 years or so, it has been increasing very fast. And in the past about 60 years, the increase has been exponentially rising. So that's kind of a worry for us. And we also give the numbers, like what was at the AR6, AR5 cycle, like maybe about 10 years back, and the concentrations today. So you can see how fast these concentrations have increased, and actually these increased rates are actually at the highest level in the all our history. So it's really that the anthropogenic activities are actually pumping these greenhouse gases into the atmosphere. And we do further analysis now that we have much more denser and accurate observations. So if you do the reconstruction, we cannot get the, for example, the location specific information, because they have in the polar ice contain the very averaged information for the greenhouse gases. But now we have for last 60-70 years, we have in situ direct observations of CO2, and which first started by at South Pole by Dave Killing, and now we have also Mauna Loa about similar time. And you can see that the Mauna Loa site in Hawaii, which actually basically is sensing signaling and getting the signal from the northern hemispheric biosphere and then anthropogenic activities, and the South Pole is getting integrated information to the South Pole, north and south hemisphere together combined. So the effect of CO2 concentration, you can see that it's increasing very smoothly and less variability from year to year. The small wiggles you see, they are actually showing the within a year variability. And so there is in the Mauna Loa, the prominent flux variability is that the summertime drawdown and wintertime release of CO2 to the atmosphere. And what you notice here for the anthropogenic signal is that in the 1960s, if you see that the South Pole concentration values were about the middle of the summer-winter variability of Mauna Loa. But in the recent times, you see that the Mauna Loa values are always above the South Pole values, which means that there's something happening in the northern hemisphere. And we can see that the seasonal cycle did not change so much, but the concentration has offsetted. And this kind of a signal is shows that there is some fossil fuel emissions which are going on, and it is taking the base values or the interhemispheric gradient to a net positive value. And we can also see that there are hint. So these CO2 observations are done by Dave Killing, and the Sun Killing started making observations of oxygen in the atmosphere. And as you know, that fossil fuel is burnt, and then fossil fuel burning consume oxygen. So there should be a signal that oxygen has to go down in the atmosphere. But oxygen, you know, it's very high amount in the atmosphere, not like CO2, which is very small amount. It's easy to measure, but oxygen is difficult to measure, and for its change, which is very small compared to CO2. And so then there is a very difficult measurements, and it measures the ratio of oxygen nitrogen, and we can prove that the concentration of oxygen is actually going down in the atmosphere. That means there is a burning occurring in the atmosphere. And then we also have in the CO2 itself contains two different stable isotopes. So carbon 12 is the most prevalent in the atmosphere, in natural atmosphere. About 99% is 12C, but there are also heavier isotopes, 13C, in the atmosphere. And if we can measure these things in now within the CO2 molecules. So then if you now extrapolate this concentration towards the pre-industrial time, you come up with a value of minus 6.5 per mil. It's actually per thousand, you can say. And then this concentration actually is going down in the atmosphere, because the fossil fuel itself has a 13C in values. It's depleted until minus 28. So if you're mixing the air from the fossil fuel consumptions with the industrial air of minus 6.5, it has to go down, as we have been emitting more and more fossil fuel. And this is also an emission kind of estimation for us. It can give us estimation, but we have much better knowledge of what is going on from the industries. So for example, we have been like burning coal, oil, and gas, and other ways of getting energy, so resources. And then we have a method. Now people have developed method to estimate from the inventories, like how much is used for different different emission sectors, and we can estimate the emission from the activity, like how much you actually are using it, and then the emission factor, because each of the species, each of the chemicals we are burning to produce energy has a different kind of energy versus CO2 emissions, energy production versus CO2 emissions efficiency. And then we also improve the technology, because you know the cars running today are not same 100 years back, or even the power plants have improved efficiency. So there is also emission reduction efficiency which goes into the calculations, and then we can estimate how the CO2 emission has happened for the fossil fuel. And you can see that for today's atmosphere, we are actually emitting 12 petagram of 10 petagram of carbon into the atmosphere every year. So this is not CO2. If you, it will become 37 or 38 if you make in the CO2 units. So all sorts of things we take into account to prove that we are causing, the human activities are causing the global warming. And now we also have to understand again which country doing what, and then how they are changing. So there is also statistics to produce the data, where you can show that okay, the emission from US or Europe probably are going down, but then China emissions are increasing, and same thing for India is also coming up in the list. So it's now fourth largest or third largest emitter behind China and the US per country. So but then these emissions are also be very interesting to understand, because so the emission reductions we see in the EU or USA are not really exactly happening for their improvement in the technology, but many of the manufacturing have now shifted to China, and manufacturing sectors produce a lot of carbon dioxide. So this, some of the share of carbon production manufacturing of items in China actually are a kind of a embedded fossil fuel emission for different country product use. So on many things are in being analyzed, understanding, and because all these things we do to figure out what is the best possible way to reduce greenhouse gases, and who would be like a, for example, there are talk about carbon taxes. So how do you put carbon taxes on the goods and services, etc. So all these things are being studied. And for us, we have we try to estimate greenhouse gas emissions, as I was told in my introduction, is that we use a approach which we call a top-down approach. And these are being developed using the CO2 concentration measurements. And it's not only two sites, we have many more sites to estimate the gases concentrations. But as I was saying, that we need to have a solid foundation of science to prove that what we are doing in different regions should be like validated using the independent methods and processes. And here we put two different processes of estimation of CO2 budget in the regional scale. One is called bottom up, so where we put like all the vegetations together, all the soil together, all the fossil fuel I just showed. So and then try to estimate what should be the atmospheric CO2 concentrations. It does pretty well, but then it's not completely. I'll show you that it's not perfectly doing the simulation of CO2 because our understanding still not complete. So this is why the top-down inversions techniques becomes important, because atmospheric CO2 observations are very, very accurate. We are measuring this concentration at 0.2 ppm accuracy in 400 ppm. It's extremely high precision measurements, and we have the all inter-institute calibration factors and everything scaled out. And then we can actually calculate the CO2 concentrations based on different emission inventories. But in this case, the method problem is that we only estimate the net exchange. We cannot separate what kind of soil or vegetation or river basins and all the things. All the things are added up together. So that's the limitation of this thing. But it gives you a, I'll show you that it gives a good information, because we need to have a global stock take. The global stock take is supposed to be done this year for the first time, and it's a project of UNFCCC in order to track the nationally determined contributions or the Paris Agreement and the Paris Agreement's progress. So these numbers are needed to be given to the UNFCCC from the countries, from the independent agencies, and we are part of one part of this system. And we would like to improve this estimates and provide information. And so this is what the inverse model or top-down system looks like. So you start with bottom-up fluxes from fossil fuel, forest, fires, and oceans, and then try to put all the fluxes into a transport model. And then you can calculate, so you mix it in the atmosphere and the transport and everywhere. And then you can calculate the concentration, which is a kind of blue line here. And we call them like simulations. And then we have the observations I was talking before. And so we have many observations, and one is shown here. And then because there is a gap between the model simulations and observations, we need to do some statistics, very simple statistics to estimate the fluxes from 54 land regions and 30 ocean regions in our case. And we are using 50 observation sites of the measurements. So we choose these measurement sites because of their very long record, and also without data gaps and high quality. So and then these calculations helps us to provide fluxes at the country level or the subcontinental level, and discuss the scientific the carbon cycle system, because some places are drought oriented, some places are temperate, some places are tropical. So different regions behave differently, and we try to understand those mechanisms of carbon's exchange. But the problem in this case that we have let's say 54 regions, the sites are very few, so that it's an underdetermined system, and then we have to make a lot of approximation for the parameters in these equations. And we have been using only one parameters settings for so far, but in the recent times, very recently, we have moved to using multiple and ensemble of inversions. So in this case, we have done 16 inversions, and then starting with very different bottom-up estimations. So we start in one case, the CO2 flux. The negative means that flux is going into the Earth's surface from the atmosphere. So 0 means that it's neutral. So the biosphere, the land biosphere is not taking up or releasing on the annual mean basis. And another case, we are giving a very strong sink on the Earth's surface and with interannual variability. So by doing the inversions, we get all the lines which you see here, colored lines. But then there the range is very narrow. But even if you have start with a very flat CO2 concentration, CO2 flux for the land, we actually derive all the values comes down to a mean values which is around the black line here, which means that our observations are actually independently providing an information how the global land fluxes should change with time with variability. So this is a very important message and information for us, and it raises our confidence that our system of estimation of CO2 fluxes are working. And then so we also estimate these fluxes, obviously, as I showed, and we can then now divide into, so in this case what I have divided into the 15 land regions. So each bar set is showing the fluxes for one regions. So I think it's too busy plot not to see too much. So the global fluxes, obviously it's the CO2 and land CO2. The land is kind of a net sink of CO2 or negative fluxes, but then there are different flux estimation in this case. So I have the bars are in one group, and then the symbols which is derived from our inversions. Generally, they're very good agreement, so they are falling in the same uncertainty range. But for some of the regions, for example, Europe or Russia, our estimations are going outside of the error bars of the other estimations. So which means that there are some regions we have a lack of confidence. So we are thinking at one hand that bottom up and top down estimations reconciliations, but in this case we are also actually interested to reconcile the different top down estimations, and we are not fully able to reconcile, which means that we still have to work on this, and we are working on this, and the progress has been happening in my research career already in last 20-25 years. But then that does not prohibit us to understand many things. So one of the things we just recently did was that how is the signal of CO2 in the high latitudes, for example, the permafrost region, or in the non-permafrost regions in the Arctic regions. So here the blue area is the permafrost region, and the green in the light blue area is the non-permafrost region. So then how is the CO2 flux changing, for example, in this area? So if you put the invert model results into this kind of a scheme where the net flux uptake trend, like how fast is the CO2 flux is increasing, uptake increasing with time, and that with tree cover. So tree 0 means it's more permafrost like, and tree cover 100% means it's more like a non-permafrost areas. So in the what it shows that in the permafrost areas, the sink or the increase or uptake increase is happening faster in this region. And similarly for the temperature range, MAT is like a mean air temperature. So if you see that the cold regions are actually experiencing faster increase in CO2 uptake, because we understand the Arctic region is actually warming much faster than the mid latitude and the low latitudes. So the response in the high cold regions is faster for CO2. And then again, if the permafrost extent is higher, then you have a faster increase in the CO2 flux uptake. And you can now go down, because here is the annual mean, then doesn't tell you much about the processes happening. Now we can separate them into 3 different seasons. One is early growing season, which is the red symbols here, and in the late growing season is the green signals here, and then the symbols here, and the winter is the blue here. So the changes is not happening in the winter time, but you can see that in the summer time, the early growing season, the spring to summer, that the CO2 plus uptake increase has been uniformly happening at all tree cover regions. But what happens in the for the late growing season, the high tree cover regions are actually losing also carbon in the faster rate than before. So on the net, we see that the net fluxes, which on the annual mean sense, it is lower than the low tree cover regions. So this kind of understanding is actually are coming out for us, and then they are very, very important information, like how the ecosystem behaves, how the sequester in the CO2 assimilation capacity of the each ecosystem changing with time under the global warming world. For sake of completeness, I just wanted to also show you the CO2 for the ocean, and we also have the ocean region fluxes. In this case, I'm showing the 11 regions, and fortunately for the ocean, it's a slow-moving pool of carbon. So then our estimation quality is much better, because you can also measure the PCO2 in the ocean and the water, and from the differences you can calculate fluxes for ERC exchange. But which is very, very difficult for land. It's not possible, and even if it's possible, it's very variable with time and space, because it's a fast changing pool. So so it's difficult. So ocean is much easier for us, and you can see that the reconciliation between the different top-down estimations are very, very good. So they are all following in the very narrow range of uncertainty. And it's anyway, the global ocean actually is sequestrating about 30% of the CO2 from the atmosphere, which is most significant part is removed by the ocean compared to the land. And we do a lot of research on this. And then, so as a whole, so you might just to complete my ocean story, that in the ocean acidification is another big issue for us, because CO2 going into the atmosphere, ocean, it's increasing with time, and then this CO2 has to go through the acidic formulations in the carbonate form, and that is creating the reducing the pH in the water, because of the H plus radicals you can see here. But this is also the process for the formation of KCaCO3, which is the calcium carbonate, which is kind of a storage of carbon from the anthropogenic emissions. And so the measurements also shows everywhere that there is a decrease in pH with time, and pH means we are getting from acidic to basic to acidic form of CO2. So why I also talk about that thing, and then is that we want to understand the whole carbon cycle and the climate feedback. And we discussed about the emissions. So fossil fuel emissions are about this is the mean of 1960 to 2019. So the numbers will be different from what I showed before. So then you can see that there is about if you see the whole emissions, 82% is coming from the fossil fuel, and then 19% from the land use change. And then the sinks, we can see that the oceans and the land are actually uptaking about 56% of the CO2 which is emitted to the atmosphere. And then there are about 44% actually remaining in the atmosphere. And sometimes we define this as airborne fraction. This is a matter of concern for us. So for example, if the one concept we are now discussing is that carbon neutrality, right? So carbon neutrality means the airborne fraction has to be 0. So nothing will stay in the atmosphere. So as much the emission should be almost equal to the sink, and ideally the sink and the sink has to increase and emission has to decrease, because the emissions are so much linked to our lifestyle. It is not very easy to reduce emissions instantly. With fossil fuel, we need for many years to come, and but on the same time, we can also have a capacity increase in the land management and the ocean management. So the idea is that in the future, in the next years and decades, we want to increase the sink of CO2, and at the same time you can to reduce the emissions of CO2, so that we can reach to a place where the emissions and sink will be balanced out, and then our at least we should be able to achieve the flattening of the CO2 concentrations in the atmosphere. And so to do this kind of thing, because as I said, that the Arctic region, the carbon sink is increasing, some places it's not increasing and decreasing. So to understand the whole thing, we need to run the Earth system model, how the ecosystem is going to behave in the future. And for that, the IPCC people have, they run various modeling simulations, which is interactive models for the socio-economic pathways, and they produce scenarios what kind of CO2 emissions would happen in the future, depending on what kind of policy we take. So you can take a sustainability policy, taking the green road, so you can start reducing emissions immediately and go to very low values or negative emissions very quickly by, let's say, 2050. And then the middle of the road, sometimes you can say that, okay, it's difficult to achieve and we can take slightly slower path, but still we need kind of this kind of emission reductions going to the negative level so that we can stabilize CO2 concentration increase, and at the future we can to reduce it. But there are possibilities that we don't do anything and we do a business as usual, and we can be in a dangerous situation. And then by doing those kind of simulations, we can summarize the results. As I said before, that about 56% of the CO2 emitted by the anthropogenic activities are taken up by the land and ocean. So only 44% remained there, right? So 56% is absorbed by that land and ocean. Now that all these 5 scenarios of the emissions I showed you, from using those scenarios, we can see how much of the uptake will happen in the future. And here, so if you the two green and the blue, and this blue and these two cases, which is the cases when the uptake by the land and oceans are above 56%, which means our land and ocean ecosystems remains healthy to uptake the remove CO2 from the atmosphere, which is emitted for the anthropogenic activities. But the moment you fall into SSP2, SSP3, or SSP5, we are actually absorbing less and less fraction of the CO2 emitted from by the anthropogenic activities, which means we are actually going into the runaway global warming scenarios. So all sorts of things has to be taken into account when you are thinking about how you plan the future scenarios. And then we come out with some very simple metric, although the things I showed you is very complicated in the regional scale, and then we can still simplify things for the communication and for the policy making. So here what I'm showing you is that, so you can make a very simple metric, how much of the gigaton CO2 we can emit to increase the 0.45 degrees centigrade temperature, for example. So there is of course range, because the different models have a different sensitivity, but roughly this is falls on the linear scale, line for the CO2 emissions versus temperature increase rate. And so we want to basically have a target to how much where we want to limit our, we are already at 1 degree centigrade in warming. So at what warming level we want to stop. So depending on that, we have the remaining carbon budget. So we are already here, and at this time, 2020, and then we only have this much amount left to be emitted. So we already emitted this much amount. Only this much amount is to be emitted if you want to achieve this level. This much is left if you want to achieve this level. So we are actually already in the very dangerous situations, because as you saw in the emission plot, we are now emitting about 40 petagrams, 40 petagrams, 40 gigaton of CO2 per year. 40 means within 15 years we are able to consume all this. 10-15 years we are able to consume much of this remaining carbon budget, which is very dangerous. And so the emission reduction should happen almost immediately. And again, so in the process of understanding how you want to improve the regional budget and assessments, and how to make policy, so we are coming out with the very different kind of framework, and where you account for fossil fuel emissions, ecosystem metabolism, biomass burning, or also including the trade. For example, I was talking about the trade which is by the manufacturing goods. You also talk about the wood trade and food trade, and all sorts of things has to be accounted for between the regions when you discuss about what is happening within one continent. There are more details in scientific studies which are going on under the regional carbon cycle assessment and processes, and these will be published for each section. So we will have about 10 land chapters, different regions, part of the globe, and then also the ocean. And from our activities, we are also running many models in Japan, from bottom up and top down studies, and it is under our own projects funded by Ministry of Environment. And then we are providing this information on yearly basis to the UNFCCC, so that this kind of information can be used for CO2, methane, or N2O, and we can and then these kind of efforts are done by every country, and we come together and share information for the global stock take in principle. So here are my kind of take-home messages. So concentrations of CO2, methane, and N2O have increased very significantly in the past 100 to 100 years, and also it's rising very fast in the very recent times. Let's say since year 5. So then we also have an anthropogenic CO2 emissions, and then we have a regional patterns of them. So which country and how is driving how much emissions. Then the natural fluxes we also are still sometimes remaining uncertain, but then we also are gaining confidence by various simulations and estimation by inverse modeling. And the global warming feedback remains obviously very sensitive issue. We do not really have the, for let's say example, the very sophisticated models we would like to have to include all processes, but they are still our system models. There are ways to improve them, and we are now giving more information on the region specific or the ecosystems level information, so that better models are produced for the future studies. Yeah, then we need of course the urgent policy measures. Then all the policy between the countries and the processes all has to be taken into account when you make the most effective policies. Yeah, with that I'll stop, and thank you very much.